Hi, my name is Calvin Murdock, and today I will be presenting the paper Dataless Model Selection with Deep Frame Potential, which was written with my advisor Simon Lucey while I was a PhD student at Carnegie Mellon University. Deep learning has all but overtaken the field of computer vision, but despite numerous groundbreaking results, we still lack a fundamental understanding of what exactly makes it work so well. Why are some deep neural network architectures consistently better than others across applications, ranging from image classification to self-driving cars? To answer this question, we observe three key components of state-of-the-art architectures. First, adding more layers reduces generalization error without overfitting, even when the number of parameters far exceeds the available training data. Second, residual connections, like those in ResNets, improve performance without any additional parameters. And finally, denser skip connections, like those in DenseNets, improve parameter efficiency, allowing for even lower generalization error. The difficulty in explaining these observations has made principled deep model selection challenging. We attempt to approach this problem through connections to sparse approximation theory, which provides tools for analyzing both the capacity for memorizing training data and the capacity for generalizing to unseen testing data. Unlike deep networks, shallow representations have a bias variance trade-off. As the number of model parameters increases, the output necessarily becomes more unstable, leading to worse generalization performance. So what exactly is the difference between deep and shallow learning? Shallow representations can be constructed as a single layer of an affine transformation followed by a nonlinearity. Deep representations just compose many of these layers together, but shallow representations can also be inferred by minimizing reconstruction error. Nonlinear structure comes from optimization constraints such as non-negativity or sparsity, instead of nonlinear activation functions. But constraints are typically much easier to deal with than explicit nonlinearities. Specifically, we consider the constraint set C that consists of representations W that are non-negative and sparse, having low L1 norms. The nonlinear projection onto this set is exactly the rectified linear unit. This allows us to approximate the solution to this non-negative sparse coding problem using thresholding pursuit, which is equivalent to a neural network layer. If the dictionary atoms are orthogonal, the solution is exact, but more generally, when can the solution to a sparse coding problem approximate a neural network layer? It turns out that this feed-forward approximation is accurate when the dictionary has small mutual coherence, which essentially measures how far it is from being orthogonal. In addition, this also guarantees uniqueness for better memorization of training data and robustness for better generalization to testing data. As the number of dictionary atoms increases, they must be packed closer together. With more parameters, the minimum achievable mutual coherence increases, and so generalization performance worsens. But what about deep representations? We approximate feed-forward deep network activations as solutions to multi-layer non-negative sparse coding problems. Additional layers correspond to additional terms in the objective function. This can equivalently be expressed as a higher dimensional shallow model with block structure that depends on the deep network architecture. Adding layers to a feed-forward neural network increases the number of dictionary atoms, but also the effective dimensionality of the system. In comparison to shallow dictionaries, where model expressivity is increased by adding dictionary atoms, the dictionary structures induced by deep networks are more square and have a fixed structure of non-zero elements, allowing for lower mutual coherence. However, the lower bound now also depends on the dictionary structure. So are there other structures that can achieve lower mutual coherence with fewer parameters? In fact, yes. Denser dictionary structures have lower mutual coherence with smaller dictionaries and fewer learned parameters. In comparison to incremental chain-structured deep networks like AlexNet, denser skip connections that rely on all previous network activations induce denser dictionary structures for lower mutual coherence. More generally, the activations of many architectures can be approximated as non-negative sparse coding problems with certain induced dictionary structures. For example, the identity connections in residual networks induce identity dictionary blocks for lower mutual coherence without any additional parameters. And the skip connections in dense nets induce additional blocks of learned parameters for even lower mutual coherence. In comparison to chain networks, which are shown in yellow, ResNets in red and dense nets in blue can have lower mutual coherence with fewer parameters. A similar trend also appears for CFAR10 validation error, where skip connections improve parameter efficiency. This correlation suggests that a lower bound on mutual coherence effectively predicts the benefit of depth and skip connections and can be used as an efficient proxy for validation error in deep model selection. For more details, please refer to our full paper. Thank you.